Prior to that, Lennart and Michael had carried out a long and difficult analysis of these maps. And one of the ways to translate the fruits of their analysis into a statement describing what one actually sees is to construct SRB measures. I'll say some more about that later on. Okay. I was flattered to be asked, intimidated by their 100-page manuscript, but realizing there was an important project, I signed on. Okay. Well, this SRB project finished in 2 or 3 years, but I continued to get to know Lennart better in the time that we spent together at UCLA. I value enormously the relationship that developed, not just mathematically, but in a very personal way. Some part of the mathematics that I will report on today was inspired by this seminal work of Lennart and Michael, and I will make explicit the connection when I get there. Okay. So here's an outline of my talk. The part of dynamical systems theory that deals with chaotic phenomena is called hyperbolic theory. And within hyperbolic theory, one could further distinguish between an abstract theory or general theory and the application of this general theory to concrete situations. And my talk will touch upon both parts, but it will have more to do with the second than the first. Okay. Now, today's topic is a subclass of hyperbolic systems called strange attractors of rank 1. Okay. I will tell you what these objects are, about their dynamical profiles, where they occur, how to detect them. Okay. And the main examples that I will use to illustrate these ideas come from periodically forced limit cycles and Hop Bifurcations in ODEs and in parabolic PDEs. Okay. So my talk then is divided into 3 parts, quite naturally. It's really the third part that I'd like to report on. The third part is about the detection of strange attractors of rank 1 in periodically forced ODEs and PDEs. Okay. But in order to tell you, in order to explain this part, I have to first tell you a little bit about the objects that I'm talking about, hence the second part of the talk. And this being a general audience lecture, it's probably better to go a little bit farther back to provide some context, hence this very first part. Okay. So this is the outline of my talk, and I will mention the works of many people. As far as my own work is concerned, my main co-author for parts 2 and 3, from here on down, is Chiu-Dong Wang, and one of the main co-authors for an example that I would like to spend some time on in this third part is Kuning Liu, in addition to Wang. Okay. So I now begin on this with a 15-minute introduction to general hyperbolic theory. I have the option to introduce the concepts in discrete time or continuous time. Continuous time meaning differential equations, and the discrete time dynamical systems are defined by the iteration of a map of a space to itself. I'm going to say it in discrete time. So here, capital X is a phase space or a state space. Think of each point in this set as representing a state of the dynamical system. And I will be take a point in X, little x in X. A transformation F from X to itself represents the transformation of the state X with the passage of each unit of time. And the sequence X, F of X, F of X, it's a composition, not a power, and so on. It's called an orbit of the dynamical system. A set of orbits that attracts all nearby orbits is called an attractor. So here, this is an impressionistic picture of what an attractor might look like, is the red part. And a set of initial conditions that are attracted to the attractor is called its basin of attraction. So attractors are invariant sets, compact invariant sets. One thinks of them as relatively small objects. They're very important because they capture the asymptotic behavior of a lot of initial conditions. The basin of attraction, on the other hand, is large and is perfectly visible, is open and is often open and is perfectly visible. Okay, so as the meaning of hyperbolicity, I'm using it in a way that is synonymous with local instability. Okay, local instability equals hyperbolicity. So in its pure and most idealized form, you can think of a hyperbolic map as looking like this. This is the first 3 points of an orbit. The picture is locally saddle-like. The expansion representing the instability. There is contraction because if you're on an attractor, for example, it's volume decreasing. So if there's expansion, there's contraction. Okay. Now, a much more flexible way of describing a local instability is the presence of positive Lyapunov exponents. Okay. Lyapunov exponents are numbers lambda with the property that if you take a point x in the phase space, look at the nth iterate of the map in a certain direction. If this differential, if the derivative in the direction v grows like e to the lambda n, then lambda is called the Lyapunov exponent at x. Okay. So positive Lyapunov exponents means there is exponential separation of nearby orbits, hence strong sensitivity, sensitive dependence on initial conditions, and so on. So these are the ways in which hyperbolicity manifests itself. Now, in this talk, I want to distinguish between two kinds or two levels of hyperbolicity. The first is the presence of many complicated orbits, and the second kind is a much more pervasive kind. The first kind, the presence of many complicated orbits, is usually embodied by Smale's horseshoe. Okay. This, many of you have probably seen this logo of a horseshoe map. A horseshoe is a stretch and fold mechanism. You take this green box and you stretch it horizontally and then fold it back onto itself. When this picture is present, it can be shown that there are many orbits. Okay. If you label the two branches of the horseshoe as heads and tails, then it can be shown that orbits whose itineraries correspond to any sequence of heads and tails are present. In other words, there are as many orbits, different orbits, as there are when a coin is flipped infinitely many times. So this is what I mean by the existence of many complicated orbits. And these orbits are all unstable. Okay. Now, even though there are many different orbit types and many complicated orbit types, the presence of a horseshoe does not tell us anything about what happens to the typical initial condition or to most initial conditions. In fact, it's entirely possible that this horseshoe is present and yet almost every initial condition, the orbits would eventually tend to a stable equilibrium. When that happens, we say that there is transient chaos in the system. The second is much more sustained and observable kind of instability, is characterized by positive Lyapunov exponents almost everywhere, Lebesgue almost everywhere, or at least on positive Lebesgue measure sets. In this, by observable, I refer here to almost every initial condition. And by sustained, I refer to the fact that the derivative growth in the positive Lyapunov exponents is sustained in time. Okay? It doesn't stop. In this second kind of instability, there are no stable equilibria. The instability continues forever. Okay? And as I mentioned earlier, when you see a horseshoe, it can be the second kind, or the chaos can be transient. But the second kind is much more sustained in time and observable, meaning is happening everywhere. Okay. So it's the second kind of that I like to focus on. Okay. And one of the ways to prove that you have the second kind of dynamical complexity is to construct something called SRB measures. So this is a very important concept, so let me flash the definition by you, even though for purposes of this lecture it's really better to think of it as something else. Okay? So the definition of an SRB measure is like this: is an F-invariant Borel probability measure with a positive Lyapunov exponent mu almost everywhere, and with smooth conditional measures on unstable manifolds. So this notion was introduced by Sinai, Ruel, and Bowen for XMA attractors, for a class of attractors invented by Smale in the 1960s. And this concept was extended to much more general situations beyond XMA by Lennart PA. I was also part of that. Okay. Now, maybe a good way to think about SRB measures, at least for purposes of this lecture, is the following. Okay? If mu is an ergodic SRB measure with no zero Lyapunov exponents, then for all continuous observables phi defined on the phase space, the trajectory averages tend to the average with respect to mu for a positive Lebesgue measure set of X. Okay. I'll let you stare at that for a moment while okay. So the interpretation of this theorem is as follows, that SRB measures are really the measures that one observes in the following sense. You have an attractor, which, as I said, it tends to be quite small, has zero Lebesgue measure, but its basin is large, and you can see its basin very well. So you take a typical point in the basin, and you look at, say, the first 1 million iterates of the trajectory, first 1 million points in the trajectory starting at X. Now, if you give mass 1/1,000,000th to each one of these points, then you form a probability measure, namely this object here. This probability measure is a good approximation of the SRB measure, if such a measure exists. Okay? And that's what that theorem there says. Okay? I want to emphasize that it is not the Birkhoff-ergodic theorem, even though you see a trajectory average and a space average is not the Birkhoff-ergodic theorem, because Birkhoff-ergodic theorem says that mu almost everywhere something happens, but here the invariant measure lives on the attractor, while we're talking about a positive measure set of points in the basin of attraction, far, far away. So SRB measures are singular measures singular with respect to Lebesgue. They have rather small supports, and yet they control the behavior of orbits starting from the entire basin, far, far away from the support of the measure. Okay. So these measures, when they exist, are definitely the objects that one observes. Unfortunately, we don't have a very good understanding of when these measures exist. Okay. Sinai, Ruel, and Bowen discovered and constructed SRB measures for XMA attractors, and quite a bit is known about these, the general properties of these measures, but the question of when they exist and when they don't, in general, is not very well understood. It's one of the wide open questions in hyperbolic theory. Well, let me mention at least some of the properties of SRB measures. Okay. Suppose you take an observation. Say you have a dynamical system describing some physical process, and phi is, say, the temperature of the system, for example. And if you take the temperature at day 0, day 1, day 2, day 3, and so on, that forms a sequence of observations. This can be viewed as a sequence of random variables, defines a stochastic process with underlying probability, SRB measure, mu. Okay. Now, the idea here is that if this dynamical system is sufficiently complicated, then the dynamically generated sequences of this kind would also behave like genuinely random stochastic processes. For example, one could ask if a central limit theorem holds. One could ask if it has exponential decay of correlations or polynomial decay of correlations. dynamical systems being deterministic processes, one usually doesn't have independence. So, but still one could ask, if you look at the measurement on day n, look at the covariance between that and the measurement at day 0, does the system forget its past exponentially fast, polynomially fast, and so on. Okay. As it turns out, for chaotic dynamical systems, for hyperbolic dynamical systems, the answer there's a very wide range of possibilities. And here is a summary of a few results that tells you how one could determine which is which. So this is a very rough statement. Okay. It says that if you take a reference set with a hyperbolic structure and look at the return times to this reference set, okay, these are not necessarily first return times, but they are good return times, then what determines the statistical properties is not how soon the first parts return, but how soon the last parts return. Okay. So M here is a reference measure such as Lebesgue. If you look at the set of points that has not returned by time n, so the tail of the return time function, in other words, if the tail dies down exponentially fast, then this system has exponential loss of memory. If the tail dies down a little bit faster than 1 over n squared, for example, then a central limit theorem would hold for this dynamical process, and so on. Moreover, there is a direct relation between the geometry of the dynamical system and the tail of this return time. So this brings us to the end of the first part of my talk. It's not an in-depth discussion by any means, but I hope I've given you some general idea of the general flavor of the subject, the issues raised, questions asked, partial answers, and so on. Against this backdrop, I now move to a more concrete set of dynamical systems, which is a subset of all hyperbolic systems. Okay. So let me begin with a very concrete example, the Hénon maps. Okay. The Hénon maps is a two-parameter family of maps of the plane given by these formulas. Well, first there are some easy facts. Okay. For certain parameter ranges, it has an attractor, and it has horseshoes. These are fairly easy facts to establish. But beginning with the simulations of Hénon, one already started to observe a very sustained kind of dynamical complexity, sustained kind of chaos. And for a long time, there was no mathematical results to explain these observations for more than 10 years, until the result of Benedicts and Carleson in 1991. Okay. So what Benedicts and Carleson proved was that for positive measures set for b bigger than 0, sufficiently small, there is a positive measure set of A. So A and B are the two parameters here. Okay. Near 2 is a perturbative result. Okay. The HAB, so for these good parameters, HAB has positive Lyapunov exponents along certain important orbits. Okay. I have not tried to give a very precise statement of their results. In fact, no description, no one-page or 2 or 3-page description of the results will do it justice, in the sense that what they did much more. What they did was to identify what is important, devise some complex machinery to track the derivatives of these important orbits, and to inductively construct the good parameters. This is genuinely seminal work. It contains ideas that, when suitably generalized, go considerably beyond the specific setting of the Hénon maps, which is what was studied in this paper. Okay. And building on the analysis of Benedicts and Carleson, Benedicts and I, that constructed for the same parameters here, SRB measures. This is the result I alluded to at the very beginning. To my knowledge, it was also the first time that SRB measures were constructed outside of the XMA category. There was a number of other results that followed, building on this first result of Benedict's and Carleson, including results by Benedict, Viana, and myself, but I will not go in that direction. Okay, so from this point on, I'm reporting on mostly, but not exclusively, joint work with Chiu-Dong Wang. And let me first tell you what our goals were, what we had in mind before we started. Okay, what we wanted. So this is a project that started several years ago, and our first goal was to identify a natural class of attractors with geometric characteristics similar to a norm. The fact is that in dynamical systems, there are many attractors that appear to have folds that look similar to a norm. And the question is how to mathematically put them together under one umbrella. Okay? And that was the first goal. And if we could do that, then naturally we would like to develop for this class of objects a dynamical profile. For example, what type of statistical properties do they have, and so on. And thirdly, it became increasingly important to me that I didn't want to just isolate a class of maps and develop for it a dynamical theory. I wanted to try to make some connections to other parts of dynamical systems and other parts of mathematical sciences that use dynamical systems as a tool. Okay? And for that reason, I wanted very much to have checkable conditions that, when verified, would allow me to say that if I know for a fact that that attractors with this and that properties exist once I verify a certain list of conditions. So it's very much with this mindset that we started on our project several years ago. And the class of attractors that we came up with can be summarized as follows. I would call it rank 1 with instability. Okay? And let me explain a little bit what I mean by that. Okay? So these attractors can live in phase spaces of any dimension greater than or equal to 2. And by rank 1, I mean something along the following lines, that the derivative of the map at any one point, which is a linear map, has the form of rank 1 linear map plus something small, something relatively small. This means in particular that there is at most one unstable direction. Okay? Now, it's natural that these attractors would be more amenable to analysis because these are in some sense strange attractors of the simplest kind. Okay? Well, what do I mean by that? Okay? Well, if it does not have any instability, then it wouldn't be strange. It would be like a limit cycle. You wouldn't call that a strange attractor. So it has to have some instability. But there's at most one unstable direction, which is the minimum that it can have. So in this sense, these are the simplest strange attractors that there are. The Hénon maps with B small is an example of the rank 1 attractor with instability. Now, I don't mean to mislead you by telling you that these objects are simple to analyze. They are not. No strange attractor is simple, but among all strange attractors, these are the simpler ones. So my results with Wang has the following form. Okay? It's given a two-parameter family of maps, f of a and epsilon. Epsilon is the epsilon there, is the amount of contraction. Okay? Satisfying conditions C1, C2, and so on, which I will tell you about later. Okay? Then the following holds for all positive small epsilon, that there's a positive measure set of A such that these Fa epsilon has an attractor with properties P1, P2, and so on. Okay? So of course I haven't told you very much other than the form of the result. I will tell you what these conditions and the result and the properties are momentarily. One could obviously, the more conditions one imposes, the more properties would can be concluded. Most of this is already completed work with one small paper to be completed. Okay. So starting with the P1, P2, and so on. Here is here's a sample of what these results can be. First and foremost is the existence of SRB measures. Then there's a bound on a number of ergodic components. See, what SRB measures do is that they organize the phase space, the basin, into some large pieces with coherent dynamics. A bound on a number of ergodic components tells you how many such pieces there are. Okay. There's control of almost every point in the basin. Central limit theorem on the ergodic components. Exponential decay or correlations on the mixing components, and so on. There's more. One could say symbolic dynamics, symbolic coding of orbits, bounds on topological entropy, and so on. Okay? So this is a sample of the results of P1, P2, and so on. Well, how did we come up with this set of properties? Well, I was motivated by two things. One is the availability of techniques from general hyperbolic theory on the one hand, and the other is usefulness from the point of application. So it's fair to say that I was kind of shooting in the intersection of these two sets. Okay, when I'm going to show you now some examples of what the conditions C1, C2, and so on look like. I will show you 4 conditions that will imply these 3 properties. Existence of SRB, the ones with a green check mark, existence of SRB measures, central limit theorem, and exponential correlation decay. Okay. It's not important that you follow exactly what these conditions are. I won't be using them in any way, just to give you a sense of the flavor of what they look like. So here, F A epsilon is a 2-parameter family of maps from an n-dimensional space to an n-dimensional space. This n-dimensional space has one distinguished direction, which is one-dimensional. So I is either an interval or a circle across an n-1 dimensional disk. So think of it as a circle, a solid torus, or something like that. Okay. So the first condition is regularity and existence of singular limits. So here it goes. It says that for every epsilon, the map is C3. For every A and positive epsilon is an embedding. And as epsilon, which is the amount of contraction, okay, goes to 0, the map converges, the FA epsilon converges in C3 to FA 0. Okay. Now, FA epsilon are maps from embeddings from n dimension to n dimension, but as epsilon goes to 0, this map becomes degenerate. It goes from n dimension to a one-dimensional map. Okay. And this is what I mean by the singular limit. Okay. Well, by singular limit, I sometimes also refer to the following, that if you look at FA0 and restrict that to the one-dimensional part, then this becomes a 1-parameter family of one-dimensional maps. Okay? And the rest of the conditions are all on the singular limits. Okay? So you start with a map, pass to a singular limit, and then the rest of the conditions are on the singular limit. Okay? Now, if I'm to have an attractor with unstable behavior, it has to come from somewhere, and it comes from here. That the one-dimensional map, there has to be one parameter for which this one-dimensional map is sufficiently expanding. That's C2. C3 is a transversality condition that says that when you turn the parameter A, you can change the dynamics effectively. So don't worry too much about what I've written down here. What it says is that suppose the critical point of this map lands on a fixed point, then when you tune the parameter, the critical value and the fixed point has to move at different speeds. Something that is true almost unless there are some rather unpleasant coincidences. Okay? And then there is a last condition, which is non-degeneracy. It says that, well, this map is an n-dimension to one-dimensional map. I don't want it to be completely degenerate, so the norm has to stay away from 0. Okay? So this is a type of conditions that I have in mind. With these 4 conditions, the 3 properties with a green check mark would follow for a positive measure set of A. As you can see, I have tried to make the formulation rather generic, not tied to any specific formulas, to increase the range of applicability. So to very quickly interpret these results for you, what C1 and C2 say is that the geometry is right. Okay? So C1 and C2 here says potentially we are in the setting where it's possible for a strange attractor of rank 1 to occur. Okay? It doesn't say that it really exists, but the geometry is more or less right. Oh, here maybe I should say a few words about terminology. Words like strange attractors or chaotic attractors have no formal definition in dynamical systems. One should really be aware that I shouldn't say no two people, but there's no widely accepted definition, and people tend to use these words completely differently. They are really mostly descriptive words. However, they're extremely useful descriptive words. So for the rest of my talk, when I say strange attractors, I will mean strange attractors with this type of properties. I'm going to use it as a shorthand to mean, when I say the word strange attractors for the rest of this talk, okay, I will mean strange attractors with this type of properties, strange attractors of rank 1 with this type of properties. And when somebody else says that these words, they are quite likely to mean something different. Okay. Usually not quite as strong as what I have here. Is that this is strange attractors in a very strong sense. Okay, so back to these conditions, what C1 and C2 say is that potentially the geometry is right for the presence of strange attractors of rank 1. And what the theorem says is that if the geometry is right, and if there are no bad coincidences, for which you have to check C3 and C4, this involves checking some conditions at a finite number of points, okay, then such attractors really actually are present. Okay. So first, you have to be in the ballpark. That's what C1 and C2 guarantees. Then you have to pick up your pen and check a couple of conditions. And if that too check, then the attractors are really there. Okay. I also want to mention that when these results are applied to specific situations, one is generally not handed the system F A epsilon. There is a differential equation, as you will see momentarily. And the idea is to try to embed the systems of interest into a system of this kind, which has a meaningful singular limit. If you succeed in doing that, then you can back up from the singular limit and obtain the results that you want about the systems of interest to you. Okay. And finally, I want to mention the role. I want to comment on the role of A. So epsilon is the contraction. This is what allows me to pass through the singular limit. But why introduce a parameter? Why not just take a system and determine if it has an SRB measure? The answer is you can't. Okay? The reason that you cannot is that for systems of this kind, it takes infinite precision or knowledge of an infinite number of steps to infinite precision to know whether or not a system has an SRB measure. Of course, it's totally impractical to iterate, to go to infinite precision. So one can only, the best that one can do is to say, well, under these circumstances, it's with positive probability, strange attractors with this and that properties are present. Well, how to say positive probability in a function space, in the space of dynamical systems? One way to do that is to put on a one-parameter family. Okay, so that's okay. So I now move to the last part of my talk, which is on the detection of strange attractors of rank 1. And I remind you that when I say strange attractors, I mean attractors with the properties that I mentioned earlier. Okay. I like to talk about 3 different scenarios. I don't want to call them 3 different applications because they are essentially the same body of ideas, which manifests itself in several different ways. So the first scenario is the periodic kicking of limit cycles. Okay. So first, I'll mention an abstract theorem. Take a C4 flow on a manifold in any dimension. Suppose there is a limit cycle, an attractive hyperbolic limit cycle. Then there is a positive measure set of kicks. You just disturb the system in some ways. There's an open set of kicks such that if you first kick and then let the system flow for time t, look at this composite map made by kick, flow, like that. Okay? So you drive it, and then you just relax and let it flow for time t. Okay? This composite map has a strange attractor for a positive measure set of t. T is relatively large here. Okay? It is a positive measure, and it is roughly periodic with the period of the cycle. Okay. So this is an abstract result. It says that if you take a limit cycle, you can always drive it in some ways and cause these strange attractors to happen any limit cycle. But let me show you a concrete example of this. So suppose first that, so maybe I want to cover up this part also. Okay, so I'll cover up this part first. Okay, so this is the world's simplest equation describing a limit cycle. Theta is in S1. Y is 1 dimension, so lambda is positive, so y equals to 0 here is a limit cycle. Okay, so y equals, theta just goes around, y equals to 0 is a limit cycle. Okay, now to this limit cycle, I now add a kick. Okay, the kick is to drive it, so I have a limit cycle going around like this. I will drive it up, down. Okay, but with the sine function, I have used a delta function for kicks. It doesn't really matter. You can use continuous kicks if you like. The important thing is a long relaxation time in between. So the kicks take place at time 0, capital T, 2t, 3t, and so on. And the result is that if sigma over lambda times A is bigger than a constant, then this holds. Then the ft, which is the time t map of this equation, has a strange attractor for a positive measure set of t. So what exactly is this constant here? Sigma is the shear, lambda is the contraction, and A is the amplitude of the kick. So if this number is large enough, then you are more likely to have strange attractors. Well, this is quite natural that if you kick harder, then of course, so A is natural. If you kick harder, then you are more likely to have strange attractors. The work is really done by the shear. It's really done by sigma, which has to be non-zero. Lambda is the contraction. So if you have a very strongly contractive limit cycle, it's very robust. It's hard to break it. If you don't break the limit cycle, you're not going to turn it into a strange attractor. So if you have a weak limit cycle and strong shear, and that's the right setting that is conducive to having turning a limit cycle into a strange attractor. Okay, so C is a number that, unfortunately, I did not have a precise value for. It's a medium-sized number. It's not extremely huge. Okay. It's 10, something like that. It has to do with a sine function. If I change to a different function, it will be a different number. Okay. So the second scenario is slow-fast systems. And this page and the next is joint work with John Guggenheimer and Martin Wechselberger. Okay. So slow-fast systems are systems with 2 or more incommensurate time scales. Okay. They are given by equations of this form. Okay. And one generally studies these systems by looking at the slow manifold defined by S equal to 0. So in this picture is given by this cubic surface here. So away from this slow manifold, the flow moves very, very fast towards it. And once it gets close to the slow manifold, the flow moves rather slowly along the slow manifold until at some points it may jump off and jump to another branch. And it may jump off and then move very quickly to another branch. Okay. Now, this type of slow-fast systems are very naturally associated with rank 1 attractors. Okay. For example, if I make some simplifying assumptions, such as all trajectories on the slow manifold eventually jump, and there are no canards. Canards are solutions that when they get to the edge of the slow manifold, they make false moves. They kind of look like they're jumping, but then they sometimes change their mind, go back, and try again later. Okay. So suppose we let's eliminate these more complicated kinds of behaviors. Then the section map for a section like that naturally has a rank 1 attractor, which is not necessarily unstable. It's not necessarily strange. So from what I have said so far, it could simply be a simple limit cycle. Now, for folds to be created, it's very easy. That if you look at the top sheet of that cubic surface, and suppose you're looking at it from the top, okay, and L1 is the curve where all the trajectories are supposed to jump off. Okay, this is the jump curve. Okay, and if I look at the slow flow, the flow induced on the slow manifold by the equation, okay, then this second line L2 here is the where in the limit as epsilon goes to 0, the jump from the bottom sheet lands. Okay. Okay. If you look at the slow flow, and on this second line, where the jumps from the bottom sheet is supposed to land, if the flow doesn't move in directly, but instead it kind of moves in and out like that, and that is enough to form a fold in the singular limit map. So the singular limit map is in fact really just the section map or Poincaré map from this line to that line. Because the flow does this, you can see that these 3 points will all be mapped to the same point, and a fold is formed. In fact, a strange attractor of the kind that I mentioned results if this map from phi 2 to phi 1, the section map following the slow flow is sufficiently expanding. Okay. With Guggenheimer and Wechselberger, we carried out numerical verification of some of these conditions, in fact more of them than the ones that I showed you. This is Van der Poel's equation with a slightly different forcing than that used by Van der Poel to eliminate the Carnots. So one of my points here being that even though this is a differential equation with 2 different timescales, in order to check these conditions, since our conditions involve only the singular limit, this involves only integrating a differential equation of a single timescale. In fact, you only integrate the slow flow from this line to this line, and it involves a finite number of steps to verify these conditions. Iterating the return map for a finite number of steps to verify these conditions. So now I get to the scenario 3, which is periodically forced Hop bifurcations, and here my co-authors are Wang and Liu. Okay. So to motivate the setting, let me first ask you to think about an equation of this kind. Think about a partial differential equation of a generalized reaction diffusion type, where x here lies in a bounded domain in Rd. The u is a vector in m-dimensional vector, and D is a diagonal matrix with positive diagonal entries, and, for example, Dirichlet boundary conditions. Okay. My main assumption is that u xt equals to 0 is a solution. Oh, this is by the way, I forgot to say this is a 1-parameter family of PDEs parameterized by mu. Okay. And there is this solution, u xt equals to 0, is stable for mu negative, and at mu equal to 0, it loses its stability. This is how the Hop bifurcation happens. And to this equation, I will add the forcing of the following kind. Okay. So this is the forcing term added. Rho is the magnitude, is a constant, is the magnitude of the forcing. Phi of x is some function, is quite arbitrary. And P of t is a forcing that has the form of an impulsive force. It again doesn't have to be exactly like that, but most of the driving happens in a quite localized way, and then there is a long relaxation time. It's really the long relaxation time that I care about, not the particular form of the forcing. Now I'm going to view this dynamical system, view this equation as a dynamical system on H10 crossed with itself m times. That is actually a special case of what I would like to consider. I like to consider, in general, an evolution equation of the form u dot equals au plus f mu u plus a forcing term. So that's being a special case of what I have here, where u is some element of a Hilbert space. Negative a is a sectorial operator. Think of it as a Laplacian, if you like, but I actually allow the spectrum to open up in a sector with some control at infinity. F mu and phi can actually be smooth functions on H sigma, which are the fractional power spaces of H. And as before, I will assume that 0 is a stationary point for all mu, and I'm going to call f sub t the semigroup for this force equation. And I will choose to view the semigroup as being defined on H sigma. Now, I'm now going to give you the precise statement of the theorems. So there are two assumptions. There are exactly two assumptions. The first is that the unforced equation, i.e., without this term, undergoes a generic supercritical Hopf bifurcation at mu equals to 0. And the second, which I might as well first, second is on the forcing term. So let me say first that what I mean by Hop bifurcation means that if I define a sub mu to be a plus the linear part of f of mu, okay, which you could think of as a polynomial, for example. So you take the linear part out, and so this operator has the property that its two lead eigenvalues cross the imaginary axis, okay, at mu equals to 0. Okay. And the typical picture, I would say in the next transparency what exactly I mean by generic supercritical, but the typical picture is that in a direction in the space defined by these two eigenvalues, first you have a stable equilibrium, and which turns unstable, so it starts to spiral out, but the outside continues to spiral in, and so a limit cycle results. It's a result of by Andronov and Hopf 1940. So the second assumption is that the forcing function phi, it has to carry 0 into anything but not in the space ES. Well, ES and EC is the decomposition, the splitting associated with the spectrum of A sub mu. Okay. So at A sub mu, there is an eigenspace corresponding to these two, and then there is an invariant subspace corresponding to the rest. So this is a codimension 2 subspace, and I don't want to drive 0 into this codimension 2 subspace, but anything else is fine. So it's not a very serious assumption. Okay. Okay. So now I say exactly what I mean by the generic supercritical. To do that, I go on to the center manifold, and one could write the equation out in its normal form. So the first order term is the requirement would be that the real parts cross the imaginary axis at non-zero speed, and the generic supercritical refers to a condition on the third order term. I want this third order term to be supercritical, means it's less than or equal to 0. I want it to be strictly less than 0. Okay. And these are all the conditions that I will be assuming throughout. Okay. Now there is a geometric invariant that will be very important to me. Since we hadn't seen it before, we took the liberty of giving it a name. We call it the twist number. The twist number is the third order term in a normal form of the Hopf bifurcation. If you look at the imaginary part and divide it by the real part, and that is what we will call the twist of the. All this has to do with the unforced equation. Okay, so getting to the attractors now. This is all for mu positive. Okay. In the unforced equation, it's easy to see that if you there's an annulus in the center of manifold crossed with a disk in the stable direction. There's so an open set with a property that everything in the open set, if you start with initial condition in the open set, then the solution will tend to this what I call the Hopf limit cycle, the limit cycle that appears in the Hopf bifurcation. This is for the unforced equation. For the forced equation, the forcing happens when t is bigger than constant 1 over mu, then this same this same region is invariant. It maps the time t map of the semigroup takes this region into itself. Okay, that means that once it takes it into itself, that means that there is something inside. If you keep iterating inside and taking the intersection, there is a thing there. So far, we don't know what that thing is, but this is what I'm going to call the Hop Attractor. Okay, so there is a region that if you don't force the equation, it contains a limit cycle, everything goes to the limit cycle. If you force it, it continues to be invariant, and there's something inside, and what's inside is the object of interest. So to elucidate the geometry, let me first state two relatively simple results. So here are the players. R is the radius of the Hopf cycle. If you don't force it, there's a Hopf cycle, and R is the radius. It's roughly of order square root of mu. Rho is the magnitude of the forcing. Think of the forcing as more along the center direction. Okay? And T is the period of the forcing. Tau is the twist. These are all the players that there are. And to fix the geometry, let me think of the limit cycle as a bit bigger than the than the forcing. Okay? Theorem 1: if the twist is big enough, depending on these objects, okay, don't worry too much about what this is, but if it's big enough, then the time t map has horseshoes. The attractor is complicated. It contains at least horseshoes for all large t. For t bigger than something on, the attractor always contains something complicated. Now, this means, in particular, that the PDE giving rise to this equation, to this picture, has infinitely many periodic solutions of arbitrarily large periods. Having a horseshoe, remember, means that you have orbits corresponding to any sequence of heads and tails. Okay? In particular, there are periodic blocks of heads and tails that correspond to periodic blocks that correspond to periodic solutions of PDEs. In general, it may be hard by hand to construct periodic solutions of PDE, but this type of softer reasoning gives all at once infinitely many periodic solutions of arbitrarily large periods. And if the twist is small, there's a gap between this number and this number here, then the thing inside, the Hop Attractor, is in fact just a simple closed curve. And let me show you the picture of how this happens. So the gray part is the Hopf limit cycle, and the forcing simply drives it to the side. Okay, that's all that I do. So this is the cycle, and drive it to the side. Now I relax it. Okay? As you relax it, the flow starts to take hold, and the twist number, the meaning of the twist, is that points that are farther away from the center of the Hopf cycle rotate faster than points that are inside. Okay? So points here are rotating considerably faster than points this one, leading to a tail of this type being formed. Okay. Is the twist number, the geometric meaning of the twist is the differential in angular velocity depending on distance to the center of the cycle. Okay. And so this is at time 0, this is time 3. At time 6, it has pretty much relaxed back onto the limit cycle itself, with the limit cycle itself, but with folds having developed. And then at this time, I drive it again. This picture is exactly the same as that one. I just drove it again. And then it relaxes, okay, again. And it's time now to drive it again. So you can see there's some folds having been formed. And here tau is 10. And this picture, I believe, contains horseshoes. Tau here, when it's small, means that the differential is not very big, so this fold simply doesn't happen. So these two results are relatively, they're not so hard to prove. The hard work comes with the next one, which says that this is a more serious result requiring a more stringent conditions. So if tau is bigger than the same type of constants, but the same kind of quantities, except that the constant here has to be larger. Okay? Then the time t map of the semigroup has SRB measures for positive measure set of t's. The same conclusion as before. Okay? In fact, for almost every initial condition in U is the trapping region, is an open set, and I have put a box around almost every, meaning that yes, I know I'm not supposed to say that. Okay? For almost every U0 in this open set, then the solution with initial condition at U0 has positively Lyapunov exponent, and also that the trajectory averages tend to the space average described by the SRB measure. Okay. So what this theorem says is that there is instability in this picture that is sustained in time, meaning that these, for almost every, I'll explain what almost every is momentarily, that for almost every initial condition, the solution is unstable for all times. So as meaning that solutions with very nearby conditions will diverge exponentially quickly. And almost everything is described by an SRB measure. Okay? It's sustained in time and ubiquitous in the phase space. Ubiquitous in the phase space referring to the almost every in an open set. So what does almost every mean? Since I'm now in a function space. Okay. So here it's natural to there is a splitting into a two-dimensional there's the splitting of the spectrum and therefore of the tangent space as 0 into a center part and a two-dimensional center part and a codimension to the stable part. Okay. It's a theorem that there is a C1 codimension to strong stable foliation, i.e. these green guys, okay, with the property that these two properties hold. Well, if it holds for 1 point on one of these green leaves, these green leaves are codimension 2 leaves in an infinite dimensional space. So if these properties hold at 1 point, then it holds on the entire leaf. And also they hold if you take any two-dimensional, two-parameter family transversal to these green leaves, then they hold Lebesgue almost everywhere. So this is a fairly large set. In the transversal direction is almost every, and once it holds on one leaf, it holds on everywhere on that leaf. So this is what I mean by almost every. It's perhaps not an unreasonable way to extend the idea of SRB measures, of how it describes things for a large set in the phase space to the context of parabolic PDEs. In general, one would not expect, of course, the foliation to be, it would be finite codimension, not codimension 2, and probably would not be C1, but only be absolutely continuous. I don't know if that is true, and I plan to pursue that further. So my last transparency is an application of just the previous ideas from the last few pages to what is called a brusellator. It's a simplified model of chemical reaction invented by Prigogine and Levervet. It describes a chemical reaction where UT and VT are the concentrations of two chemicals. A and B are the concentrations of two other chemicals, which are held at constant. And this reaction, so the A and B assist in the reaction of these two, and two other chemicals are produced, but they don't play a role. In this model, it's well known that U equals A and V equals BA inverse are stationary solutions, and that by adjusting A and B, the concentrations of the first two chemicals that help in the reaction, a Hop bifurcation happens. These are well-known facts. Okay. So now to this equation, I'm going to add forcing. We could do both Neumann and Dirichlet, and the forcing terms are like that. Okay. So this means the impulsive forcing, rho is the magnitude, and so this means at periodically to, by external means, change the concentration of U periodically. If you do that, then the previous results apply, and so for suitable parameter ranges, horseshoes and strange attractors with everything there happen. The main thing is to be able to arrange for the twist factor to be large enough, because that is the key to everything. In this case, we have checked that the twist factor can be made as large as one wants. In the Neumann case, which is the simpler of the two, tau in fact goes to infinity as A goes to infinity. So if you make the concentration of this chemical large, tau will be large, and the attractor will be formed. So I hope I have more or less convinced you that these attractors occur quite naturally in simple systems. Because they are rank 1, it's natural to find them shortly after a system loses its stability. So that's all I have.